All right, guys. So today we're gonna look at the January 2025 paper two solutions for physics. So let me go. Jadon, since you could talk, let me go, right? So I would like you to read question 1E.
Complete the statement below. Transformers can increase or decrease the with a corresponding decrease or increase in blank. The basic principle behind the working of a transformer is the phenomenon of blank between two windings linked by a common magnetic flux.
Oh, windings. That's windings. All right. So Jadon, you know what transformers do? From the name alone, it says transformer. So what do you think it is do? Do you remember how a transformer does work? Yes or no? Beyond. Tell me fast.
Yes,
Yes.
it has worked. It has worked with the principle of in
In mutual induction.
yeah, me too, right.
So
I
we're
was
gonna
gonna say induction alone.
um they might consider that, but the key thing here is mutual induction. So that's the answer for this part. And what does it do with the voltage you put in?
Is it does give out the exact amount of voltage you're putting.
No. Well, here how
So
a transformer does work. Well, here how it does work. Depending on the number of turns in the primary and secondary, it will either increase the voltage or drop the voltage. Well, I shouldn't say drop the voltage. I should say decrease the voltage, right? So, Jadon, let me just say you put in 500 volts here. If it's a step down transformer, you might get like 50 volts or just something less than 500 volts. Yes or no?
yes, sir.
Okay, so while we're doing this, I'll give a little crash course on transformers. Transformers does work on the principle of mutual induction. We know that. Another thing, can transformers work on direct current?
No,
Justin?
sir.
No, Justin. Justin, why can't transformers work on direct current?
because it need alternating current to move the coils, right? For the current to pass through it.
Well, current can pass through direct current, but
Well,
what to induce a EMF, you need a what kind of magnetic field? A constant magnetic field or a change in magnetic field?
change in magnetic field.
Right. So we're gonna use AC voltage to generate a change in magnetic field. And if we want to figure out how much the voltage is increasing or decreasing, it's very simple. All we're gonna look at the ratio. You could either look at NS over NP or VS over VP. So this is one of the main things you need to remember. You need to remember NS over NP is equal to VS over VP. So Jaden, do you know what NS means?
So like step up.
Nah. NS means the number of turns in the secondary winding. So you see this? This is called the primary winding. So all winding just means you're winding wire, right? You're winding wire in a solenoid. This is what it means. All right, Jaden? That's what winding means. So this you can see
Yes,
here, as you can see here, you have one winding, and over here you have another winding.
yes, sir.
So this is the primary winding, and this is the what do we call that?
Secondary wire.
Right. Awesome. And what do you think VS means? Since you know that NS is number of turns in the secondary, what do you think VS is? So at least what does the S stand for? What does the S stand for? Jadon, don't overthink it. What does the S stand for? Can I hear you, Jadon? Justin, what does the S stand for? What does VS stand for?
The voltage in the secondary
Right.
thing.
And VP stands for the voltage in the primary. So let me understand something. They say in here that transformers can increase or decrease what? What, Justin? What could it increase or decrease?
The voltage.
Right. But we want to be extra specific, right? What kind of voltage transformers does work with, Justin?
AC.
Right? So we're gonna say it could either increase or decrease the AC voltage, because if you put DC voltage, you're not gonna do anything. So we want to be specific with a corresponding decrease or increase in. So Justin, let me go through a fundamental law for this. If I'm Justin, if you study plenty for your exam, you're gonna do good or you're gonna do bad.
I'll do good.
So if I in so shouldn't the input power be equal to the output power?
Yeah.
So I would just say the power in the primary should be equal to the power in the secondary. And how do I find power? Power is equal to what by what?
IB.
IV. So this is going to be IP, it's going to be VP, and that's going to be equal to IS, VS. So Justin, I have a question. Let me give you a little example, right? So like, this looking like a step down. Well, it is a step down, right? And how do I know it's a step down? I know it's a step down because the number of turns in the primary is a lot more than the number of turns in the secondary. So Justin, let me give you a little example. Let me just say we have 500 watts on the primary, and if this is an ideal transformer, no losses, how much watts should the output be given out?
The same amount.
It should be given out the same amount, right? And so
Yeah.
essentially, if if I had 500 volts, how much current would I have in this winding? What by 500 would give you 500 watts?
Um. The
Remember, power is equal to V by I. Power is equal to V by I. P is
with the
equal,
current by voltage.
right? And we don't know what the current is, but it's not hard to figure out. If the power is 500 and the voltage is 500, what would the current be? Or would I have to multiply by 500 volts to get 500?
1.
Right. So the current going to be 1 amp. So you understand that. Since it's a
Yeah.
step down transformer, what's going to be stepped down?
The voltage.
So let me just use an arbitrary value of 50 volts. 50 volts. And let's just say that, well, we'll figure it out. Justin, since I decreased my voltage and I still had to get 500 watts,
Yeah.
I still need to get 500 watts. So what is the new current then? What would multiply by 50 to give me 500 watts?
10. 10
Oh,
amps.
so by increasing the what's in? By decreasing the voltage from 500 volts to 50 volts, what increased?
The current.
Right. So I think you're seeing the answer now. I think you're seeing the answer for sure. You had to be seeing the answer. So if you increase or decrease the AC voltage, there will be a corresponding decrease or increase in
Current.
current. Yes. Vade, I need to know if you're okay with this. Let me know. Can I hear from Vade? Jiran, are you okay with
Yes,
it?
sir.
Okay, Vade, I hear. Nice, nice. Jiran, are you okay with this?
Yes, sir.
Okay, cool. Let's move on. So I'm gonna show you a big life hack over here. Hear what I'm saying. So Jiran, if I wanted to figure out how much my voltage on the output is gonna be, look at what I could do, right? You see this ratio over here?
Yes, sir.
3,960 to 600. What does that mean? That means we have 3,960 windings in the primary. And how much windings do you think we have in the secondary?
600
Right. So where do we have more windings?
in the primary.
Anytime you have more windings in the primary, you have a step down. So I'll make a note about that. So more turns, and I'm not writing this for style. Please copy it down, guys. So more turns in primary means step down. If you have more turns in secondary, it means that what you done?
A step up.
Right. I go explain the concept. I'm not sure if I'll ever get it, but essentially, the more turns you have in your coil, the more magnetic fluxes are going to cut it, and the greater the induced EMF. So the greater the voltage is going to be. So if I have a few coils over here, only a few of the magnetic is good. The coil is going to cut, but it wouldn't cut as much as if it was more turns. And so the induced EMF, which is the voltage in the secondary, would not be as much as, say, if you had more turns. Because the more turns you have, the more interactions it's going to have with the magnetic flux. And so you'll get a greater EMF. So Jadon, the less turns you have, that means you're going to step down the voltage. The more turns you have, you're going to step up the voltage because it's going to cut more of the magnetic flux and you'll get a greater EMF. So I hope you understand this, yes or no?
Yes, sir.
So watch this, right? Let me just say I wanted to figure out what I could multiply the primary by to get the secondary. This is what I could do. I could say 600 all over 3960. So I want you to plug that into the calculator and let me know what you're getting.
So 5 over 33.
Tell me it is a decimal.
0.5, 0.151.
Okay, we go round that off to two decimal places and that'll be like 0.15, right?
Yes, sir.
So Jaron, what if I tell you we just now find something that's very, very important? You gonna believe me?
No.
No? Well, watch this, right? So what happened in here is, you understand that this is a step down. So any voltage I put here on the output is going to be less. So let me just say I had an input voltage of 500. According to what we just now find, what would I do with that 0.15 if I wanted to figure out the voltage across the secondary? What could I do with that 500?
So multiply by 500.
No, multiply by the 0.15.
Well, yeah.
So the ratio, so the turns ratio, right? The turns ratio is an indicator of the factor of multiplication. So if I want to figure out how much I would have in a secondary, I'd multiply 500 by the turns ratio. So try it. So say 500 by 0.15.
So it'll be 75.
Right. So Jalen, you see what happening, right? So essentially, we just now found a constant there, 0.15, that we could use to multiply any value here to figure out for the voltage in the output. So we can kind of see how the transformer behaving. You understand?
Yes, sir.
So if I put 500 volts here, I'm going to get 75. Justin, if I put 600 volts here, how much am I going to get on the output?
With 600 volts there.
What? Someone again?
But it has 600 volts in the first one, right?
Right. I have
So it'll
600
be
volts,
60 on the other.
60 on the other side? No. Remember, you have to multiply that by
Yeah.
the turns ratio. The turns ratio, let's tell you what you're going to get in the secondary. So multiply
It's
600.
600 by 0.15.
Yeah.
90.
Right. So please keep that in mind. Wait, please keep that in mind. If you want to figure out what you're going to get in the secondary winding, you find the turns ratio or the ratio between VS and VP, and you multiply it by the input. Wait, yes or no? Let me know if you understand that.
Yeah.
Yeah, okay. So I can't blow all in mine, eh? I'm blow all in mine. Jaden, watch this. So Jaden, they give me some values over here. And in case all you're wondering, anytime all you see this arrow here, that means it's a variable, whatever it is. So if I see this, that means it's a variable resistor. That's what the arrow means. It means I could adjust the it means I could adjust the value, right? So Jadon, you think that this table should follow this relationship? Yes or no? Tell me, Jadon.
Yes, sir.
It should, right? So
Yeah.
the same table 1 shows values obtained for V2 and V1 when varied from 0 to 80 volts. So we take any input and we're going from 0 to 80 volts. So Jadon, let me try our thing now. Let me try our thing. Let me just check if what I have in the table is correct. So Jadon, give me a voltage, a input voltage from the table. So we're looking at V1. Give my input voltage.
20.
20, all right. So if I have an input voltage at 20, what am I supposed to get in the output? According to what we know. Tell me, Jadon, if I have,
So multiplied by the 0 point
yeah, do that for man, tell me what you're getting. I'm
so
V,
three.
you're getting 3, and look at what they had in the table. What they had.
3.1.
We could try it for another one if you don't believe me. Let me try it for, say, 60, right? Multiply 60 by 0.15 and tell me what you again.
9.
Whoa. So if you look at that, and you see that again, 9, when you put 60, and they record that they got 9,
Yes, sir.
yeah, isn't that cool? So you're getting to see if like the values in the table make any sense. So now you know what to do with them, right? Justin, let me try one. So Justin, give my input voltage
Um,
from the table.
input voltage. Um,
So we already
45.
okay, you're going to use 45, all right, no problem.
Yeah.
And so if I wanted to figure out the voltage across the secondary winding, how would I do that? I would say 45.
45 by 6.7.
No, remember, Justin, if I want to
Mm-hmm.
get the voltage in the secondary, you're always going to multiply it by the turns ratio. So multiply 45 by the turns ratio, which is 0.15 in this case.
Okay. 6.75.
6.75. Is that close to what they got?
Yeah.
So is everything making sense? Is everything
Yeah.
making sense? So are the results behaving like how the transformer is supposed to behave? Yes or no?
Yes. Yes.
Yes. The
But
transformer.
in a question like this, where the terms ratio is be on top, right?
All right, so I will tell you. They don't always give you the turns ratio. Sometimes they might give you the secondary voltage and the primary voltage, but you need to understand something. The turns ratio is just the number of turns in the secondary divided by the number of turns in the primary. That's one way you can do it. And that's also equal to the voltage in the secondary divided by the voltage in the primary. So I'll show you something, right, Justin? So
Yeah.
Justin, check this. Let me just say we choose 60/90. So remember what the formula is saying? The formula is saying that NS over NP is equal to VS over VP. And that's what the formula is saying.
Yeah.
So what was NS over NP? What is the number of turns in the secondary divided by the number of turns in the primary? We found out earlier. What was that?
0.15.
Okay, so I'm going to show you something, right? So we're saying that that's
Mm-hmm.
supposed to be equal to the voltage in the secondary divided by the voltage in the primary. So what's the voltage in
Right.
the secondary for this circle,
Voltage in secondary is 9.0.
right? 9.0. And that'll be over what? V1 is the
60.
60, right? What is 9
Yeah.
over 60? Plug that into your calculator.
Okay. 0.15. Oh,
Bam. So you see everything
yeah.
making sense, right? Everything making sense here. Nothing crazy going on. So what I'm saying is, you have two ways you could find the turn ratio. If you want to find the turns ratio, you need the first thing you need, well, you need the number of turns in the secondary, right? And you need the number of turns in the primary. If you don't have that, then And let me just say you have Vs over Vp. You could use this as well because they're equal to each other. That's what I'm trying to say. They're equal to each other. Yes or no?
Yeah, I understand now.
Okay, good. So let's plot our graph, right? So Jaden, before we plot anything, we have V2 versus V1. So V2 versus V1. What comes first, V2 or V1? Tell me, Jaden, which one comes first, V2 or V1?
V2.
V2, whichever one comes first, we're plotting that on the y-axis. Whichever one comes second, you're plotting that on the x-axis. So we want to obtain a graph of V2 versus V1, right? And this is a graph that has to pass through the what? If you look at the first values, 0 and 0, that suggests that the graph will have to pass through the what? What is 0, 0 called?
So the axis.
The origin.
Oh,
The origin. We call it the origin. Think about it. It makes sense. That 0, 0 is like the origin. That's like where everything coming from, right?
yeah.
So we want to get a graph that looking like this. So the hardest part of this question might be to come up with the scale. So I will help all you come up with the scale, right? So Jaden, you in charge of helping me come up with the scale on the x-axis, and Vade, you in charge of helping me come up with the scale on the y-axis, because I know you're real smart and thing, so I want to challenge you a little bit, right?
Oh gosh, sir.
Yeah.
Yes, we hope so.
The people on YouTube go see her, you know what I mean? They will see her, right? Right. Let me write this out a little neater here. Okay. What the hell? All right. Wood. Yeah. Let me get the table real quick. So we have the table here. So Jaden, let's figure out a suitable scale on the x-axis. Again, we are plotting V1 on the x-axis and V2 on the y-axis. So Jaden, what is the smallest value on the x-axis?
Was 0.
0. So we had to start at 0 and we had to go up to what value?
10.7.
Nah, if you're looking at the wrong thing, V1 on the x-axis. So I look in here.
Oh,
Yeah, sure you understand that.
yes, sir.
All right. So the smallest value is 0 and the biggest value is 70, which means we need to come up with a scale that will at least take up more than half of the page. In physics, whatever graph you draw or come up with must be taking up more than half the page. So Jaden, try to figure out a scale I should use.
So every 2 blocks could be 10.
I like what you're thinking, yeah? That'll be 10, 20, 30, 40, 50, 60, 70. And we could probably put 80 here if you want. All right, so we go with that? No problem, right? That was easy. Now I go and call Vade. Vade. I'm gonna see you. I'm gonna see you in action. Let me see about this.
2 centimeters to 1 unit.
Okay. Give me a second, man. I still a little sick. Those running. All right, let me keep pushing, right? So you see, you tell them that every 2 centimeters is 1 unit, right? Let me see if that works now.
So, yeah, didn't tell you wrong.
Oh shucks. Damn. That's crazy. I see now I'm using 3 over here. My bad, gang. All right.
I wonder what I to say.
Let me just double check.
So,
Oh
so
my
one
God.
off.
I would just shift the whole thing. If I shift the whole thing, that wouldn't work either because they would just be displaced. Oh no, it worked. Right? Yeah, that looking correct. And I just put 1 over here as well. So wait, let me count now and see if we cover the full range. So this could be You want to call this? You want to call that 1?
We'll call it 1.
With 0.1. We want to go from 0 to 10, eh? Well, really, like 11. You really want to call it 0.1? Because, like, this could be, if we say in that, this could be 0.1, 0.2, 0.3, 0.4, 0.5, and this could be like 1. I don't think that'll cover the range 0 to 10. Vid?
See, I said 1, not
Oh,
0.1.
I thought it says 0.1. Sorry. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Vid, we run into a problem. Is that gonna cover 10.7?
It will
Nah,
not.
10.7 gonna be like over here, right? God.
What if we just use the same scale, but we move the block down once and put the kind of squiggly line?
You can't do that. You can't. You know why you can't do that here?
Full
This graph,
circle for
this graph has to start at the what?
That's at 0, so
Exactly. Anytime your graph has
so,
to start at 0, you cannot cut the axis. Make a
yeah,
note of that, right? Make a note of that.
it's just a number.
So here what? Maybe we could try to scale down a little bit. So we're gonna leave the same 2 centimeters. But what if I say this is 1.5? I'm not breaking any rules here if I say that. And if I say another is 1.5, what would this be?
2.
So you understand what I was saying? The scale of 2 centimeters to 1 was not fitting. So maybe we could try 1.5, which is slightly bigger than 1. Slightly bigger than 1. So maybe, so obviously it will take up more space, right? So you'll get a wider coverage of values because you start off at a bigger value. So 1.53, some of it,
1.5, 3, 4.5, 6, 7.5, 9, 10.5, 12, 13.5.
so does this graph take up majority of the space that we needed to?
It would.
It's good, right? So I feel like that would have give a little trouble. I think in the exam, this would have give you trouble. Yes or no? Wait, did you do this paper?
I skimmed through it and I did all the answers mentally.
Mentally, you say. Okay.
But I did write it on to talk it out somewhere.
All right. So let me just write down the main points, right? So since V1 is on the x-axis and V2 is on the y-axis, I could write down the main points. So that'll be 0, 0, 10, 1.5. You continue.
20, 3.1, 30, 4.7, 45, 6.7, 60, 9.0, 70, 10.7.
Right. So I could get rid of the table now since I have all the points I need. Judah, do you remember this from the yesterday classes? How to figure out the points from the table?
Yes, sir.
Okay, good. So before we move on, let's figure out what one of the small blocks is equal to. One of the smallest increments is equal to on either axis. So Vid, let's do that. So you have 10 small blocks going from 0 to 1.5. So 10 blocks would be equal to 1.5. Now, yeah, you could just divide by 10, but I'm just showing it for anybody that might not be able to see it immediately. So using a little bit of algebra here, you would see if 10 blocks is equal to 1.5, and 1 block would be equal to 1.5 divided by 10, and so that'll be 0.15. Wait, yes or no?
Yes.
So this is 0.15. And if every 1 block over here, if you have 10 blocks altogether, what would 1 block be equal to?
What do you mean?
Okay, so we're going from 0 to 10, 0 to 10, so that's 10, and that 10 is divided amongst how much small blocks? So how much small blocks we have here to here?
Yeah.
10. So 10 divided by 10 is 1. So one of these small blocks is equal to 1. So we could say 10 blocks is equal to 10. So one small block would be equal to 1. Okay, so we have everything now. We can start. Yeah, so Vade, the first one is very easy, 0, 0, right? What's the other point?
20 on the x-axis, 3.1 on the y.
What happened at 10?
Oh no, I think you zoomed in a bit.
Yeah,
10 on the x, 1.5 on the y.
right here, right? Wait, I just ran a little circle. Oh my, that's not a circle. Maybe just go with work out. Yeah, nice. So that'll be over here. Wood. Yeah, let's do some others. 23.1. Yeah, so Vade. Let me kind of see what that'll be. So 20 and 3 are stopping by 3.1. So we know that this is 3. What is going to be 3.1?
3.0, no, it's 3.15.
3.15, because we know that one small block is 0.15. And so 3.1 would be somewhere in between there. Yes or no? Right? And then we have 30, 4.7. So Jaden, now we do this one. 30, 4.7. I'm going to show you how we're going to do it, right? So I buy 30, I'm going to go up and I'm going to stop at 4.7. So this is 4.5. So then what would this, if I go up here, what would that be? Tell me, Jaden. If I were to go up, are we
6.
4.65? Because every small increment I take is 0.15. So this is 4.65 and I want to go to 4.7 if I remember correctly. So I'll go up a slight bit more. Yeah, them can really zoom in and take paper and verify that. So you're good. You're good, right? Once you show them that it is slightly above one increment, because this will be 4.65, and so 4.7 would be like somewhere in the middle, right? Cool. Justin, let's do 45, 6.7. So Justin,
Yeah.
I would like you to tell me where to stop. Tell me where to stop. So I'm going to go by 45, and 45 will be in the middle of 40 and 50.
Yeah.
So I'm gonna go up, you're gonna tell me when to stop.
About there.
Let me see. So we wanna go 6.7, 6.7. So Justin, how much this would that be?
6.15.
This would that be?
6.3.
Right, this one will be 6.45. This would be
6.5.
6.60, because 6.45 plus 0,
Oh yeah. Yeah.
so that'll be 0.6. And so this could be 0.75, right? No, 6.75.
Yeah.
And we want to get 6.7. So 6.7 would just be like a little
In
bit
between those.
before that. So that could probably be right here. Right there. Awesome. Then the other one is 6090, or 60, 9.0. So 60, 9.0. Where's that gonna go? Right, that one kind of simple. Let's do 70, 10.7 now. 70, 10.7. So just now, wait, tell me when to stop. So 70, 10, tell me when to stop.
Uh, nah.
Take
Why?
take your time, you know. So this is
How are they?
this is 10.5. All right, 10.5. We want to go 10.7, right? So this would be what? If I go up 1, I'll be 10 points?
1.5.
No. This over
Oh,
here,
it's 10.15. 10.65.
right? So this will be 10.65. And so 10.7 will be like somewhere in the middle.
Yeah.
So I could just guesstimate it right there. Cool. Does the graph look good? Does it look like it's gonna give us a nice graph?
Yeah.
Yeah, it looking so. It looking so. So I'm gonna draw a line of best fits. No. Hmm. So I want it to be like, I feel like this will work. Yeah, that could work. So Veda, I want you to notice something. Notice like some of the points, basically the points on either end are equidistant, meaning that you see that the line passing through like an average of the plot. So essentially, you have one point on this side, one point on this side, but the distances from the line are equidistant. You see in that?
Yes, sir.
So like that's what best fit means. Best fit means you do not average. If you had a bunch of points, you want to do like the average line through all the points. Cool. And so Jaden, remind me. Oh, let me just put on a couple of things, right? So we are finished yet. To get full marks in physics, you need to put a graph title. So this could be graph.
So I was not gonna ask that.
Oh, okay, okay. So this could
If
be
that's like you have to put in capital letters,
nah, this is fine. Graph of V2V versus V1V. Right? Graph of V2V versus V1V. So you want to include what you're plotting on the y-axis and the x-axis as well as the units. And then you'd like to say the scale. So we have to say the scale. Right? So we need to say the scale. Right, so Vid, what was the scale I used on the x-axis?
I think it was 2 centimeters, so 1 unit for both the X and the Y.
Nah, it wasn't the exact same I used on both. So
I
for the
did the Y
x,
axis.
so on the x-axis, it is every 2 centimeters is equal to 10 volts. In the scale, you need to put your units, right? You need to put what the 2 centimeters would correspond to. A lot of students don't do that. And on the y-axis, what was it on the y-axis, Vid?
2 centimeters equal
Equal
to 1.5.
volts. Don't forget to put what it was. Units in physics is very important. All right, so that's a full graph. I'm gonna get a full marks, right? Awesome. And anytime I'll plot a graph question, or they should know that the immediate question they're gonna ask you after is gradient. So let me get 2 points 1 time from the graph. So like just by
Uh,
looking at this, tell me, yeah?
I think you're missing something.
What am I missing?
The Y axis, you didn't write in the name for it. What it's supposed to be.
But the y-axis I said V2V.
But my bad, I'm
And
blind.
for the x-axis I said V1V. You have to do that. You have to label the axes in physics. You must. All right, so this is everything here. This is everything. So let me get 2 points 1 time to do the graph. So looking for a nice point. Okay, this one looking like a nice point here, I feel. Yeah, this is looking like a nice point. Take this. Read off this point for me. What is that point?
25 and 3.6, is it?
Yes, so that is 25, comma. So let me show you a trick, right? Notice that is in the middle of 3 and 4.5. So in the calculator, you could say 3 plus 4.5 divided by 2. 3 plus 4.5 divided by 2 to figure out what's in the middle. And you should get 3.75. Let me know if you got true. That's all like you got true. So wait,
Yeah.
here was saying, right? Anytime your answer is in between two weird values, or you could do is you could add it up. So we could say 4.5 plus 3 all over 2. And that would tell us what's in the middle. So we have 25, 3.75. And notice, guys, I did not use 0, because even though it's a safe bet, it was given, and we don't want to use anything that was given. You always want to read off points from the graph. So I have 1 point over there. Let me see if I can read off another point. Wait, I'm not realizing I make a little mistake. This is supposed to pass through 0. So let me just shift my graph real quick. See, and if I do that, this will have to okay, would. Yes, that's perfectly correct now. My bad, guys. All right, so this is gonna cut here. So 25, 3.75. And are we seeing any other points? Maybe if you can kind of ratchet it. Once it looking like our best fit, you could kind of ratchet. You could kind of ratchet, honestly. So for it, you see what I do? I shift it a little bit so you can pass through here exactly. You see that?
Sir.
You can do that, you know. So like when you're doing your best fit line, you had to make sure it looking like our best fit, eh? It had to pass through most of the points, and it had to be like the points had to be like equidistant on either side. But what you could do is you could slightly alter your ruler so that you see that it passing through some nice points. Yeah, you could do that in hindsight before you start working to make your life easier when you have to find gradients. Right? Yeah, so Vid, read off this summer, and there's a nice point, so it shouldn't be hard. That'll be
That'll be 65 and
9.75,
9.6, 9.75.
right? So that was 65, 9.75. So we have 2 points. Let's use the 2 points. Jidon, did I do anything that was confusing? Yeah, I don't know.
Nothing.
No? Justin, did I do anything at any point that was confusing?
No.
No, so Justin, tell me, what's the formula for gradient? S.
Y2 minus y1 over x2 minus x1.
You probably get fed up with this in physics. So which one you want to call y2, y1? I mean, which one do you want to call x1, y1 and x2, y2? Which one?
The 65 9.5 as x1 y1. And the 25 yeah.
So for anybody wondering why Justin didn't say that this was x1, y1, you could have, You could have. You get the same answer. Doesn't matter which one you call x1, y1, x2, y2 once you do the maths correct. So Justin, we're saying y2 is 3.75. So it's 3.75 minus y1. Y1 is 9.75 all over x2 minus x1. So that's 25 minus 65. So I want somebody to plug that into the calculator and let me know what you're getting. And Jiran, when you plug that into your calculator, your mind gonna be like, poof, you're gonna blow, you're gonna blow, you're gonna be like, damn, you're gonna be like, what?
0.15.
We used to see 0.15 before. Well, this is 0.15.
The transformer thing.
The ratio.
The turns ratio and guys, I'm gonna ask that question, right? So this was NS over NP, but the turns ratio is also equal to what over what? Remind me, NS over NP is 1. Always another way you could find the turns ratio, Justin.
PS over VP.
Right. And when you're plotting this graph and you're plotting the output voltage over the input voltage, V2 over V1, and when you find
Yeah.
the gradient and you're finding for V2 over V1, so it make 100% sense. And now in physics, you need to put your units for everything. On the y-axis is V, on the x-axis is V. Since you have V over V, wouldn't it cancel off? So you don't have any units?
Yeah.
Yeah, so you can put it over here if you wanted. So the units for the y-axis would be V, and the units for the x-axis would be, but since both of them are V, the units would cancel off. So because this is a ratio, really, anytime we're dealing with ratios don't have any units. All right. So Justin, what does the slope of your graph represent? Remember what I tell you, we just now do VS over VP. And VS over VP represents the what? The what ratio?
The voltage over the primary, the voltage in the primary over the voltage in secondary.
No, V2 is the secondary. In the formula sheet I give all you, I'll make a little mistake. It's supposed to be VS over VP. It will still work out, but the what is accepted and makes the most sense is VS over VP. So you can probably fix that. But Justin, no, it's not. That's not what I want to hear. Justin, what is VS over VP also equal to?
NS over NP.
And what is this? What is this? What do you call this? The what ratio?
Turns, turns ratio.
Right. So VS over VP is the turns ratio. That's what it represents.
Oh.
Right? Use your graph to determine the value of V2 when V1 is equal to 50 volts. And guys, we don't even have to use the graph, but they want me to use it, right? So we have to use it. But Jadon, and do we know how to figure out anything on the output? If the number turns ratio is 0.15, and we know we could just multiply this by 0.15.
Yes, sir.
Yeah. So if you multiply 50 by 0.115, you're supposed to get like you get something like 7.5. So let me see if the graph gives us that. So on the graph now, you're gonna draw a vertical line. You're gonna draw a vertical line at 50. And Jadon, does everything make sense? Does the world keep spinning?
Yes, sir.
Yeah, nice. And we get any 7.5?
Yes, sir.
I'm telling you, once you fully understand everything will be like, damn, well, all of this linked together. That's crazy. So it's 7.5. Calculate the current I2 in the secondary windings when V1 is equal to 50 volts. So in the secondary winding, let's look at what we have. In the secondary winding, we have a 5 ohm resistor, right? We have a 5 ohm resistor. Okay. So they want us to calculate the current I2 in the secondary windings when V1 is equal to 50 volts. So they're giving me V1. They're saying V1 is equal to 50 volts. And they want us to, and we have the resistance in the secondary. The resistance in the secondary is 5 ohms. And they want us to find I2. All right. So, Jadon, you know what you were doing this question?
So it will be 50 over 5.
No, it wouldn't be 50 over 5. I hear what you're thinking, right? And you're talking about Ohm's law. You're saying that V is equal to IR, right?
Yes, sir.
But wait, Jadon, hold your horses. Is V1 the voltage for the secondary?
No.
No. So entry would need to use the voltage for the secondary?
Y-
Yeah, because
Yes, sir.
think about it. If you want to figure out the current that's across this resistor, that's passing through the resistor, and you would need to know the voltage V2.
Yes,
Yeah.
sir.
So when V1 is 50 volts, we just calculate that. What is V2?
7.5.
Right. So we're gonna forget about the V1 is 50 and we're gonna write V2 is equal to 7.5. Right. All right. So let's answer the question now. So there are two ways you could have worked this question. So this is one. So Jadon, let me answer it, right? So now that I have the voltage across the secondary and I have the resistor that is across the secondary, I can now find for I. So if I want to find for I would have to make that a subject. And so I would divide both sides by R. So I would be equal to V over R. So what is the tell me, what is the voltage?
50.
I'll wait for you to correct yourself.
7.5.
Right, because where we want to find the current for, and it's primarily secondary.
Secondary.
Right. So we are finding the current so can we use V1? Ejida?
No, sir.
No, you need to use V2. And it makes sense, right? Because what was the last thing they make you calculate?
The V1.
I'm telling you,
In V.
everything linked together. You see it to be like damn. So the voltage in the secondary is 7.5, and the resistance of the secondary, since you're hooking up a 5 ohm resistor, right, is going to be 7.5 over 5. And the current you're going to get for I2 is going to be equal to 1.5 amps. Did I do anything that was confusing?
No, sir.
Okay, Justin. Justin, tell me, be honest with me, you'd I use V1? If they ask you to find the current in I2, be honest with me, you'd I use V1? You'd I say 50 over 5?
Yeah, probably.
Oh, God.
Being honest, yeah.
I appreciate the honesty, right? But if they ask you for the current in the secondary, why are you using the voltage in the primary for? Why are you using that?
True.
Exactly, right?
Yeah.
So I draw a diagram. So this was the resistor here, the 5 ohm, and the voltage across it, right? The voltage across this was 7.5, and don't forget it's alternating. Like my electrical engineering background bugging me, because when you have, I like how they're thinking alternating current so simple, but it's actually not. You actually can't use V is equal to IR for alternating current. When if any of you do electrical engineering, you'll see that you can't. And you see that you can. You'll have to calculate the imaginary parts, all kind of thing. Whew. But at this level, count all your blessings. Count all your blessings. So we have 7.5 volts AC, right? Across a 5 ohm resistor. So yeah, so you have to use V2. Nice. So let's move on. Right. So Vade, read this question for me. Read G. Because you the
So,
top G.
oh, use this slope of your graph and the equation I1 equals S by I2 to determine the currents I1 in the primary winding.
Do we know what S is? If you were paying attention, you would know what S is.
S,
What is S?
we do
What
know
was
what
S?
S is 0.15.
Right. So you was paying attention to some extent. I always looking at you, know. I always looking at you. So S is equal to, should I say bottom G? S is equal to 0.15,
No.
right? And so if S is equal to 0.15, we're also going to recall that I2 was equal to what? What was I2?
7.5.
Over 5, which was 1.5 amps, all right? And so I1 is going to be equal to S, which is 0.15, multiplied by 1.5. And so that's going to be equal to 0.225. Yes or no? Yes or no? Verify that.
Yeah,
If you round that off to 2 decimal places, which is typically what they want, you'll get what?
2.3. 0.23.
How much all it is actually write all the answer on the number line? I mean, on the line provided. How much all it is actually do that? I know I don't. You would have it like half of the time. I just pay it over here.
I don't really see it making sense now, unless it's like a one-mark question.
Yeah, because I mean, you're gonna put all the work in here, right? Why you studying to pay your answer over here when you finish? Okay, let me do part I. So, Justin, I'm gonna call you on this. Anytime they're asking us to calculate power dissipated, You typically should use P is equal to I squared R. And V, this is the formula you told me that you never saw before. This is the formula you use anytime you want to figure out power dissipated. So Justin, if we want to figure out the power dissipated in the resistor R, we're going to use P is equal to I squared R. And remind me, Justin, what was the current passing through the 5 ohm resistor?
It was
Do you remember?
1.5, right?
Yeah, 1.5. So we're going to say 1.5 squared. And what was the resistance across the secondary winding?
Um, that one I can't remember the resistance.
5. So plug that into your calculator and I'm going to weigh again for P.
1125.
Yeah, 11.25 watts. All right. And we have a 1 mark question here, Vade. Right? 1 mark question. Determining power inputs to the primary windings by the source. Let me take a double take. So they want me to figure out the input power, right? Input power. Let me see what kind of transformer we're dealing with. What kind of transformer is this?
Step down.
I'm not just a step down. A what?
Ideal.
If it's an ideal transformer, are there any power losses due to eddy currents or anything? You know about eddy currents?
What about it? Briefly.
Well, all you had to know at this level is that that's a kind of loss that has happened in the transformer. But since this is an ideal transformer, are we gonna have any power losses? Tell
No
me.
power loss with ideal.
So if it's an ideal transformer, no power loss. And if that is the case, the input power is going to be equal to the output power. And what was the output power? This is the output power, by the way, because this is at the other end. So this is the output power we found for here. If you understand what I mean, V, this was at the secondary now. So this is what the transformer is outputting across to the resistor. It's dissipating 11.25 watts across the resistor without any load being hooked up, right? So 11.25 is the output power. So if that's the output power, then the input power will be equal to
Same thing.
the same thing, which is 11.25. That's why it's 1 mark. That's literally why it's just 1 mark. Because it's an ideal transformer, no power losses, whatever you get for the output, just right back for the input. Cool, let's keep pushing. All right, I don't like these kind of questions. They're so stupid. Like, I feel like it shouldn't be in physics, man. What is doing in physics? It should be like in geography. Bro, what? You understand what I mean, Vid? What alternative energy source? Right, but let me keep pushing. I like my calculation questions. Me, I like to write. So Vid, give A part one a read.
Identify one alternative energy source utilized in or that is relevant to the Caribbean.
In my example, this shouldn't be hard.
Solar.
Solar, right? So you have solar energy, you have geothermal, you have wind energy, you have hydroelectric, you have a bunch. So I'm going to write a couple down. So you have solar, you have wind, you have geothermal, you have hydroelectric, you really have a bunch, right? So, but you just need to state one, and we decide to pick solar because that's the most obvious one, right? The Caribbean hot, obviously. Obviously, we're going to use solar. All right, Jadon, read part two for me. Jadon, read part two for me, please. Oh, Jadon in class. Oh, shucks. Oh, Rihanna, are you there? I didn't see her. How long are you here for now?
I would say like a while now.
Oh, okay, okay. You had any questions or everything making sense so far?
It was okay.
All right. You're saying that like it was bad. Have anything you want me to re-explain? Anything? Anything like I lose your bad?
Nah, you didn't.
Okay, good, good. So read part two for me.
State two ways in which alternative energy sources like the one mentioned in AI are important to the Caribbean.
All right. Tell me something. Most of these alternative energy sources, they are what? They're what kinds of energy? That's what
Like
R,
solar or renewable.
right? Because I mean, Rihanna, it's not like the sun gonna die tomorrow, right? We could always we could always use back the sun energy, right? Same thing with wind, same thing with geothermal, same thing with hydroelectric. So it's a sustainable source. Number one, solar, for instance, is very sustainable as it is renewable and will not run out. Will be fancy and will not deplete. Because Rihanna, if you bougie here, we bad. Real bad enough. That is one thing you could say. Another thing you could say is, Rihanna, in the Caribbean, we mainly depend on what? Starts with F.
Mainly depend on fossil fuels.
When you burn fossil fuels, what does it release into the atmosphere? You should have seen them ads on TV when it was small, like how the ozone getting damaged, right? So it releases carbon emissions. Carbon emissions. So if you're using alternative energy sources like solar, you don't have any harmful emissions being released into the atmosphere. So, two, they are. So, Rihanna, do you think you'd save money in the long run if you're using solar energy on a wide scale
You
application?
could, because it will be cheaper than the non-renewable sources.
Exactly, because you gotta keep on buying, you gotta keep importing fossil fuels and yeah. But with solar, it's a high initial cost, but a low cost like in the long term. So I'm gonna put that as well. So they are environmentally friendly. Example, solar energy is clean energy and does not emit carbon emissions. I could just, if I say emit carbon emission, that's sounding redundant. So I'll just say, and does not emit carbon, like the burning of fossil fuels. All right. And the last one, more cost effective. Yeah, Rihanna, you don't find this sounding like a geotest?
Yeah, I wish that they comment Geo though.
Oh, geo wasn't good.
Like, it was good. They just asked like more agri stuff, and I wanted questions come like with the earth and river and all that thing.
Yeah, right, Cora. All right, Cora. Right? Most cost effective than importing fossil fuels. Right. So that's that. That's that here. Cool. Right. Now, I want you to state the law of conservation of energy and give my example because again, we're real bad here. We know extra stuff.
This, say if it wasn't for this question, I don't think that, well, this policy question, those other two parts would just be irrelevant. But the answer would be that energy can either be created or destroyed or transferred from one form to another.
Wait, you said that the answer was irrelevant. What answer was irrelevant?
No, like if these parts of the question were there, then like the other parts of the question would just be like irrelevant to the, you know.
I don't understand what you mean. So you're saying that
Part one and two up there.
yeah, part one and two, it's not really sounding like it should be on a geo test. Like this is actual physics. And
Yeah.
yeah. So you're correct. The law of conservation of energy states that energy can neither be created nor destroyed, but only converted from one form to the other. But I was talking to Rihanna, not you. If I call you, you
Sorry.
answer, right? But I appreciate the answer. So Rihanna, did you know that that was the law of conservation of energy?
Yeah, I did.
Okay, good. Energy can neither be created nor destroyed, only converted from one form to the next. And again, we real bad, so let me get my example, right? So Rihanna, um, give my example. Give my example where there's an energy conversion.
You can repeat.
Give me an example of an energy conversion.
Um,
I feel like the easiest example is probably friction, and
I
friction. You like
was
friction?
going to say kinetic energy, but never mind.
Yeah, you can say kinetic energy. So if you have a ball, if you rest a ball on a high at an elevated surface, wouldn't that now possess gravitational potential energy? And if
Yeah.
you push the ball, it gets converted to kinetic energy, right? So we could probably say, mm, ball on top of a ramp, on top of a ramp. So this would have gravitational potential energy, and that would get converted to kinetic energy when pushed. Right. Oh, while at this, let me just go through something. Guys, this will be stable equilibrium or unstable equilibrium? Stable or unstable?
Stable.
Okay, you say stable, Rihanna.
No,
If
unstable.
so you agree that is unstable, right? Okay,
Those
Rihanna,
are two separate
Yeah,
then.
it unstable, right, Rihanna? If a hard wind blow, what gonna happen to this ball?
yeah, it'll roll off.
It could roll off, right? You don't want a relationship like this, guys. You don't want that. You don't want that. What about this? What about this? Stable or unstable?
Neutral.
No, that's not neutral. Rihanna, stable or unstable?
Stable because like, well,
If you-
unless it fall, unless the thingy majiggy fall down, then it could roll off. But other than that, it can't really go nowhere.
it really can. Oh God, this not, I'm looking at this and it look like somebody's fingernail. Oh, let's see that.
Yeah,
And this look like a WhatsApp profile picture.
yeah,
You
it
don't save
does.
somebody contact, right? So Vade, this is unstable, this is stable, and this is neutral. This is neutral. Neutral is like you rest an object on a flat surface, and so if no force is acting on it, it remains there, but it could be acted upon by a force and it could move. Think of a kind neutral.
So I was thinking that too for like the second diagram too, because if like a force acts upon that, then the whole base would move, therefore the ball inside will move as well.
I hear what you're saying, right? But what would be easier? Okay, look at this shape. The corners here are kind of trapping the ball. It can't really go anywhere. What I'm trying to say. But over here now, it's in free space. It can easily be acted upon by a force, either to the left or either to the right. I would need to put a force over here or here, which is kind of harder. So this is so Vid, what you gonna say is more stable? Would you say the ball be in here or the ball just rolling on a flat surface? What more stable?
Yeah, I think the ball being contained.
Exactly, exactly. So anytime all you're having a hard time in physics, just think about it in a common sense manner. You'll get through. So A motor vehicle is traveling along a level road. Okay, we need to underline that. If it's traveling along a level road, Rihanna, does it have GPE? Does it have gravitational potential energy? If it's traveling along a level road?
No.
No, it doesn't have any gravitational potential energy. Gravitational potential energy is the energy a body possesses due to its relative position. This is on level ground, so the height is zero, so energy will be zero. So we're looking at other types. What are the main energy changes taking place when the vehicle comes to rest after the brakes are applied? So once you apply the brakes, the kinetic energy is going to turn to what? So the car would have been moving, so kinetic energy. And when you mash the brakes, the brake pads are going to bite down and it's going to clamp and it's going to heat up because of friction. So we're looking at kinetic because the car was moving right before you, like after you press the brakes, the car is still moving. Yes or no, Rihanna? After you press the brakes, and the car still moving?
If you press the brakes, no.
No, like, okay, Rihanna, you telling me that as soon as you press the brakes, your car does stop. Like it is just immediately stop.
Okay, no. Okay. It'll move like a little bit.
It will move like a little bit. So during that process, we have kinetic energy being converted to thermal energy. And the thermal energy is a result of the friction between the brakes pad. Right?
If you put like kinetic energy to heat energy,
Yeah, that's valid. That's correct. That's correct.
okay.
That's correct. Right? Thermal energy and heat energy mean the same thing. Thermal is just sound more fancy. So I guess
Yeah, no.
I'm gonna just put that in here for anybody that might be wondering. So thermal and heat means the same thing. Wood. All right. Now this is a little tricky question. A lot of people would get this wrong. So Rihanna, let me read this question here, right? Let me read this question. Part B. Yeah, so give it a read.
An elevator has a group of 12 persons to a vertical height of 10 meters in 5 seconds. If the average mass of the persons in the group is 55 kg, calculate the gravitational potential energy gained by the group.
Okay, so let me just draw a little diagram here, right? So imagine you have an elevator. How much people do you have in the elevator?
12.
You have 12 people. Okay, so like on average, how much is where's the mass of one person? According to what they say, what's the average mass of one person?
55 kg.
If I wanted to figure out the total mass here, what I had to do?
12 multiplied by 55.
So what's the total mass in the elevator? Yeah, that's in the elevator. Should get 660, I think.
Yeah.
Okay, guys, let me ask you a question, right? If the elevator is holding 12 people, right? 12 people, would it make sense to use the mass as 55? Rihanna, do you think a whole elevator with 12 people is going to be 55 kg? Does that make sense?
No.
That don't make any sense because I'm gonna ask how much you weigh. I'll ask Vade how much you weigh, right? Vade, how much you weigh?
I weigh
Yeah, how much do you weigh?
around 120-ish, one
Like,
maybe more.
so how much is that in kg? As a physics teacher, I should know, and but I
That's
don't.
about 55-ish kilos, too, around 50 to 55.
So Vade, that being said, logically, can you say that the mass is 55 kg for the whole 12 people?
No,
You can't do that. What you doing?
have
And
to multiply it.
exactly, and we get 660. So the mass for the entire group, mass for 12 people is equal to, right? Like I said, 5 by 55 by 12, and that's 660 kg, right? And so the elevator was here, but it was here with respect to ground, but now it's up here. So essentially what you have is you would have lifted the people. Rihanna, how far did I lift the people upwards?
10 meters.
Right. Cool. And what's the formula for GPE?
M by G by H, mass
Right.
by gravity by height.
Do I have everything I need?
Yeah,
Right, I do. What is my mass?
it will be 55 by
Oh,
10.
we already finance. Wait, 55? You're gonna say 55 by 10 by 10?
Yeah,
Why are you doing that? And that would that be your final answer?
um,
Be honest with me. Would that be your final
it
answer?
be,
Say that again?
yeah. I
Okay,
say
but
yeah, it would be.
yeah. But what's the problem with that? I want you to figure out what's the problem with that. Is the mass of the elevator 55? Is the mass raising? Is the elevator raising a mass of 55 kg? What's the mass the elevator is raising?
Oh, it'll be 660 kg
Right. Mm-hmm. You understand what we're
multiplied.
on?
Yeah,
By 10, 10. So Rihanna, how come you say 55 by 10 by 10?
because it had a 55 kg.
Right, but that 55 kg is the average mass of the persons in the
Of one, yeah, of one person.
because again, logically, if you have 12 people in an elevator, that can't be 55 kg. They're talking about one person for sure. One for sure.
Yeah.
So that should give you 6,000. Jiran, are you there? Jiran here? I'm gonna check. Oh no, Jiran not here. Internet probably bugging. Right, GPE. I find GPE to sound like a rapper name. You know how it have like YNW Melly or like NLE Chopper? I don't know. I find like GPE to sound like that. You know what I mean? Like GPE. Like GPE Prime or something like that.
It was like one of those nonsensical rappers too,
Mm-hmm. No, but
like Miles.
no, but GPE Prime was hard though. If I ever become a rapper, that'll be my name. GPE Prime. Right? So that's the gravitational potential energy. So Vade, would you have had said 55 by 10 by 10?
Yeah, MGH.
Okay, and that would that have been your final answer?
No,
No, you would have to multiply that answer you get by.
the half MV squared.
What? No.
Wait,
Wait, why are you saying 55 by 10 by 10? Why are you saying 55? Is 55 the mass that the entire elevator is carrying up?
no.
No, so why are you saying 55?
So I was watching the 660 by 10 by 10.
Hmm. Nice. 660, not 55 there. Right? So let we continue. So we want to figure out power. Power is equal to energy over time. That's what power is equal to. We know what the energy is and we know what the time is. So the energy is 66,000 joules. And the time it takes to lift everybody up is 5 seconds. So you're gonna end up with some way getting. You should get 113 something.
At, at 1200.
You get 1200. How you get 1200?
Oh, wait, no. I multiplied it.
Multiply. You don't have to multiply here.
Divide. Sorry. I'm mixing my words today.
Bro's
I'm
tweaking.
not gonna sleep. I'm not gonna sleep.
That is up on, is up on. I just do that too. Right? So you're supposed to get 13,200 watts. Right? And the SI unit for power is watts. Justin, what's the SI units for charge? What do we measure charge in?
Um,
It sound like Christopher Columbus.
coulombs.
Yes, coulombs. And what's the formula for charge?
Q goes to IT.
Nice. Right, let's move on. So Justin, read this from 3A part 1.
The effects of thermal expansion can be observed in many everyday situations. List three observed examples of the effects of thermal expansion.
Right. So you ever notice like the power lines are sag?
Yeah,
Okay, let me explain something, right? Whenever you heat a metal, so whenever you heat a metal, so by heating a metal, the volume increases. Yes or no?
yeah,
All right, so when you heat, so like when the sun hot, what is the wire made up of? And the wire, and like the overhead power lines is made up of metal, like the wire.
yeah,
And so if it hot, the volume gonna increase and like the length gonna increase. And so it wouldn't be held taut anymore. It would be like sagging because like it get longer. So the first one I'm gonna say is overhead power lines sag. Another example, you ever had trouble opening a jar and you run it on enough hot water? Nah. Yes or no?
yeah,
Yeah, so that's another example. If you're having trouble opening a jar and you have a metal lid, by running the metal lid over hot water, the metal lid expands because the volume increases, and so it gets the diameter of that increases, and so it becomes easier to undo. So another example is metal lids. Right? Give my example, another example, Justin.
um, the like the material, the roads made outside, that wouldn't be one. Like the cracking of the roads.
Yeah, that's an example. So how would you phrase that?
Um,
So like you could just say
mm,
road cracks. You can say road cracks, right? So the road cracks under right. So the road cracks. Another example could be bimetallic strips. By the way, I feel like that gonna come this year, guys. Learn bimetallic strips for alarms. I feel like that gonna come. Mark my words. 5. Expansion of mercury. Um, Rihanna, and you know how a thermometer does work? Yes or no?
Yeah,
So like the
yeah.
thermometers I use a volume. When you heat up the volume, when you apply heat it, the volume expands. When it increases and such, it takes up more of the space inside of the thermometer, and so it rises. So these are some examples of thermal expansion.
And railway tracks could expand too or no?
Yeah. They could. Okay, anything could expand. Once you heat something, it expands. Generally metals, though,
Okay.
right? So we want to say railway tracks. What?
Railway tracks may expand.
You could say railway tracks deforming. Now, wouldn't deform. If you just say railway tracks, yeah, I guess you could say that. Railway tracks expanding. That's an example. All right.
And I don't know if this is one too, but my physics teacher say how the power lines could sag. Oh, okay, I didn't see that one.
That is okay. That's okay. Yeah. Right. So read part 2 for me. Yeah, Rihanna, you too. You sound like you like to read. Read part two. Okay, Rihanna, you went quiet. You went quiet on us.
Indicate whether there will be an increase or decrease in temperature in the following scenarios. Similar turn on the oven to roast a breadfruit. More thermal energy enters the breadfruit than the energy that leaves the breadfruit.
Okay, so that we. I think you know the answer, right? If you're trying to roast a breadfruit, the breadfruit gonna get hot, right? So that's gonna be what? Increase or decrease?
Increase.
Increase. From the physics standpoint, you need to understand what happens. So if you gain thermal energy, you get hotter, right? So if you gain thermal energy, you get hotter. If you lose thermal energy, you lose heat. Lose. Cool. Cool. So let me answer part B, right? So Rihanna, read part B for me.
Alicia lights a candle during the nighttime in the month of December. The windows are open and so a greater amount of cooler air enters the room than the warm air leaving the room.
So if the windows are open and more cool air entering than warm air leaving the room,
Will be decrease.
may decrease, right? Hey, Ollie didn't find rain plenty last night. It's real raining, boy. Wait, Rihanna, somebody gonna come to lock you up. Wait, and police and thing there.
No, that's India. Play music.
Okay, okay. Right? So now we're gonna call upon Justin. Justin, help me with part B. Give that a read there.
Identify the physical property that is used in the following thermometers to measure temperature.
Right.
Part 1, a thermocouple is used to measure the temperature of an oven.
Mhm. So a thermocouple is basically when you have two different metals, and anytime you heat up two different metals, yeah, you generate a electromotive force of a voltage. So the physical property here is a voltage, and I'll let you figure out the other one. So this one is voltage. Right? Justin, see if you can figure out part two. So a liquid in glass clinical thermometer is used to take the temperature reading of a sick child. That's the expansion of what? So the physical property. What if you have a liquid in glass thermometer? What's on the inside of the thermometer?
Mercury.
Right, mercury. And when you heat mercury, what happens to the mercury?
It rises.
Because the what increasing?
Temperature increases.
That's not what I want to hear. Because the increase in the temperature, what's gonna increase?
Mercury. The volume of the mercury.
Yes, and if the volume increases, then it'll take up more space. So you have to say here expansion
Ah,
of mercury. Right. Okay, so Justin, I'm gonna allow you to help me with this one. So Justin, this question for you. The next question is for you. Right. Let's keep pushing. So Justin, read
a
part.
weather balloon is deployed to observe and send information about the makeup of a volcanic ash plumes that were emitted from the La Silveira volcano in St. Vincent. Part 1. The balloon has a volume of 28 meters cubed. The gas inside the balloon is heated from 176 degrees Celsius to 260 degrees Celsius. If the pressure inside the balloon remains constant, determine the new volume of the balloon.
Okay, so we gotta use here. Charles, Boyles, which one?
Um,
Boyles, Charles, pressure, which
Charles
one?
law? Charles law?
You're making me feel like Charles chocolate now. Yeah, it looking so, right? But when you're using Charles law and the pressure law, the temperature needs to be in terms of what?
Um,
Can I use Celsius?
Kelvin.
It needs to be in Kelvin. So before I do anything, let me just write down the key information. So this will be the what? Initial or final volume. That'll be V1 or V2.
V1.
Right, that'll be V1. The gas inside the balloon is heated from 176 to 240. So this is T1, and this is,
T2.
and obviously, Justin, if you heat anything, what happens? It anytime you heat something, what happens to the gas, the solid, whatever it is? It has to E. It's what?
Evaporates.
No, well, yeah,
No, it expands. Oh,
expands, right?
yeah.
It expands. And so it'll take up more volume. So we're expecting that the new volume is going to be more than
The V1.
exactly. So see, all I could know if all the answer correct, whatever answer is you get, it has to be more than V1. Because if you heat up something, the volume is going to increase. The pressure remains constant, okay? Determine the new volume. So they want me to find for V2. That's what they want me to find for. So if you recall, Charles' law says that V1 over T1 is equal to V2 over T2. All right. And we need to convert the temperatures to degrees Celsius. Justin, how do I convert from Celsius to Kelvin?
Into this add 273. Okay.
Yep, that's exactly it. So we're just going to add 273. And so T1 would now become 176 plus 273. What are you going to get?
Oh, 449.
Say that again?
449.
Yeah. So that'll be 449 Kelvin. Brianna, when you're doing these questions, please convert your temperature to Kelvin if you're dealing with Charles law and pressure law. Please. I can't stress that enough, otherwise your answer wouldn't work out. Right, so what would T2 be equal to, Justin?
T2 will be 240 plus 273, which is 513. 513.
Right. And so let's plug in everything we have. So my V1 is 28, so I'm going to put 28. My T1 is not 176, it's 449. My V2 here is unknown. I don't know what V2 is. My second temperature is 513. So Justin, since you have two fractions on either side, what can you do?
Good. Cross multiply.
We can cross multiply. So we're gonna end up with V2. Well, 449 V2. And that's gonna be equal to 28 by 513. Right? So V2, to find for V2, I would have to divide by 449 on both sides, so it cancel off with the left-hand side. So V2 is gonna be equal to 28 by 513 all over 449. So 28 by 513 is 14364. 14364 all over 449. Let me know all again for V2.
32. Well, I rounded off.
Yeah, if you round it off to two decimal places. Two decimal places. So what's the number after the 0.99?
1.
Right, so that remains 31.99. Right, so that'll be 31.99 meter cube. Justin, does my answer make sense? Is it more than the initial volume?
Yes.
Yeah, that does make sense, right? It does make sense because it's telling us that when you heat up something, the volume expands, and that's true for Charles' law. So let's just write it down here. This is Charles' law we're using, not to be confused with Charles chocolate. Hey, is it just me or like Charles chocolate? This is cheap. I might be started seeing something controversial here, but I don't find so like anybody like any other like Charles chocolates. Everybody real quiet. Rihanna, you like Charles chocolates?
No,
I find it tastes like real.
probably because it is kind of cheap.
Well, I guess so. I like lint and like um Cadbury and
Yeah,
right. So did you understand everything I did in this question?
yeah. But if like you get a calculation, like and not all the time you have to like round it off. You could just put like the answer,
Yeah, you have
unless you ask you to round it off.
yeah, kind of have to round off. Like in physics, if they don't specify, you always round off the two decimal places unless stated otherwise. So
Oh, okay.
yeah, just keep that in mind. Right? So in part two, Vade, your time to shine, like Patrick Star. Read part two for me.
In another situation, the volume of a balloon was kept constant and the pressure of the gas was allowed to change from its initial value of 1 by 10 to the power of 5 pascals. Calculate the new pressure if the temperature of the gas inside the balloon was heated from 176 degrees Celsius to 240 degrees Celsius.
Right. So which rule is this? I think it's straightforward.
Um,
We're dealing with what here? Trying to find a new what?
P, P1 over T1 equals P2 over T2.
Right. So this is the pressure law, right? Yeah or no? Vade, you must stranded, you know.
Yeah,
Could I did it, right?
I, I don't know if it was like the mic or something, or Wi-Fi.
It's playing up real bad. Hmm. So we're trying to find for P2. So we're gonna use P1 over T1 is equal to P2 all over T2. And do we need to convert that into Kelvin, or we already know what it is in Kelvin from above?
Huh?
We already know what it is. You're on your phone on YouTube.
No, I'm not on YouTube. I'm not on YouTube.
Here's something. Catch you lacking enough. Weird. As I was looking at you, like I said, you're always doing something.
Promise you, I'm not on YouTube. I go just send a message.
Oh, right. So we
So
already know
what we
what
need to
it is.
do, we need to find the well, P1, which is the 1 by 10 to the power of 5 pascals. And we'll take the T1 and T2. Well, we have that already. So we have to do P2 be
Wait, I
equal
make
to
a mistake. I make
P1.
a mistake, guys. Sorry about that. T1 is not 513. I don't know why I write that there. T1 is 449, right? T2 is 513. So what next?
We'll have to do we have to kind of rearrange it. So it'll be like P2 is equal to P1 by T2 over T1.
Wait, I gonna arrange it one time. I'm gonna cross multiply, right? Already plug in my values. I'm just gonna cross multiply. So if I cross multiply, what am I gonna get? On the left hand side, what am I gonna get?
Yes.
So that's gonna be, I'll start you off. That's gonna be
Would it be
449.
449?
449
And
P
then
is equal to pi 1 by 10 to the power 5 by Vid. So we cross multiplying.
Right. 513.
Yes. And so if you want to find for one, if you want to find for one PT, I mean P2. So if you want to find for P2, you'd have to divide both sides by 449. So it would cancel off on the left-hand side. And so P2 is equal to 1 by 10 to the power 5 by 513 all over 449. Plug that into your calculator and let me know what you're getting for P2. Round it off to two decimal places as per usual and give me an answer in standard form.
One 1.14 by 10 to the power 5 pascals.
Right. Now, for those who do not know how to convert from to standard form, I'm gonna show it real fast. So pay attention. So the answer I got was the answer I got for this, right? It was 114,253.8976, right? And so if you want to put something in standard form, you want to take the decimal place and place it right before the first significant number. So 1, 2, 3, 4, 5. I shifted my decimal places 5 space to the left. So it's going to be 10 to the power positive 5. That's why I got 1.14 by 10 to the power 5. Right. Cool. So Vade, help me with the percentage increase one time. If I want to figure out the percentage increase, I first need to figure out the increase, right? So Vade, to find the increase, I'll compare what to what.
You'll have to do the new minus the old value, and that also have to be over the old value by 100.
Right? So I'm going to work it in parts. When you work out that, you're supposed to get 0.14. But what you said was correct. Good job. So that's going to be 0.14 by 10 to the power 5 pascals. And so the percentage increase
14.
is going to be 0.14 by 10 to the power 5. So it's always the increase over the original. The original was P1, and that was 1 by 10 to the power 5 multiplied by 100. And you're supposed to get 14%.
So,
You get 14%?
yeah.
Now, you didn't even have to use a calculator. The 10 to the power 5 would have cancelled off with the 10 to the power 5. So you're going to put 0.14 over 1, which is just 0.14. And since you multiply by 100, you shift the decimal space 2 spaces to the right. You get 1, you get 1 4. Right? So the percentage increase is supposed to be 14%. Right. If anybody confuses all the time, let me know. Rihanna, so like you understand everything I do and like every single thing.
Yeah.
Okay, good. Justin, you understand everything I do? You take
So
it.
far. So far, yeah.
Okay, good. Wait, actually no. I'm gonna rotate. Rihanna, tell me the laws of reflection.
The angle of incidence is equal to the angle of refraction.
Yeah. Now with theta I, All right, cool. And so let me give you an example of that. So just remember, let me just say that this is the boundary line. So we have a boundary line here. Remind me, Brianna, the normal is always what to the boundary line? Tell me, Rihanna. The normal is always?
The normal line lies at the same place.
Nah, the normal line is always perpendicular to the boundary line. So the normal is always 90 degrees to the boundary line. Just remember that. So wherever you have your boundary line, and what exactly is the boundary line? The boundary line is the line that separates two mediums. Remember, when we're dealing with Snell's law, we're talking about how, light would bend when it goes from one medium to another medium. So that's what the boundary line is. And so the normal is always 90 degrees to that. So let's just say we have an incoming light ray. So this is the incident ray. And so this will be the reflected ray. This is the way it will look like. And so effectively, the angle formed between the normal and the ray should be the same. So that's what the first law says. So let me know if you understand that, Rihanna. So this is theta I, and this is theta R. And so theta I is equal to theta R. Cool. Law 2. What does law 2 say?
Something about being in the same place.
Yeah.
I think.
I'll tell you the correct way to say it. So the incident ray, so you had to say that the incident ray, the refracted ray, well, in this case, the reflected ray, right? The reflected ray and the normal all lie on the same plane. And I'll draw a diagram to show you what exactly I mean by the line on the same plane, because I'm sure nobody understand what I mean.
Yeah.
Right, so I'm going to draw a diagram here quickly. So yeah, now let me just say that this is the boundary, right? This is the boundary. And what that means is, let me just say over here is air, and in the bottom is water. So you understand what I mean by boundary line? Boundary line just separates the two mediums. Yes or no?
Yeah.
Answer, Rihanna, you understand that? Well, let me just say that I shine a laser over here, and since it's reflection, it should bounce back like that. If it's reflection, and you shine a laser at this point here, it should reflect back like that, right?
Yeah.
Now let me show you something. The normal is always perpendicular to the boundary line, yes or no?
Yeah.
So let me consider a line along this plane. So this whole thing is the boundary. This whole thing is the boundary. The whole thing there, that's the boundary, and that separates the air from the water. And so the boundary line would be some line that I draw within the boundary. So you understand everything so far, yes or no?
Yeah.
Okay, we're cooking, right? We're cooking. And remember, that the normal is perpendicular to the boundary plane slash the boundary line. So can you see what I mean? Watch. See what? It kind of hard to see from this perspective, but essentially, this is what's happening. But I'll give you a really good example. I'll give you a really good example. Un momento. Un momento. I want to make sure like all you like fully understand the concept. All right, so I'm gonna put on my camera. I'm looking kind of crazy today. So this is what I'm talking about. So this is your boundary plane. This is your normal. So can you see what I mean? And so if you look at it from the side, look at it from the side, later. Can you see that the normal is 90 degrees to the boundary plane? Yeah or no?
Yeah.
And so keep that in mind. Keep that in mind. I would like you to keep that in mind. And so what do we mean when it's on the same plane? When we are saying that it's in the same plane, we're talking about the same 2D plane. So you saw the paper I just held up, right? I had a paper, and I rested it 90 degrees on a piece of paper. So check this. And again, you had to tell me if you're getting confused, right? So over here, this is a plane. This is a 2D plane. This is a 2D plane. And so the normal would be 90 degrees to the boundary line. So this would be the normal. There, right here. So can you see what I'm talking about? So this over here, this is that over there, that's the normal. That's the normal. I should probably draw it like this, right? That's the normal. And let me draw an incident ray. So let's just say that this is our incident ray. That's an incident ray. And this would be the reflected ray.
Yeah.
So look at what I'm talking about.
It
So
will reflect 90.
90 degrees, no. Because it's reflection, the angle of incidence and the angle of refraction is going to be the same. So it can be anything really. But okay, what? I'm going to do a quick diagram, well, a quick example in 3D. And you can see what I'm talking about. Do you even understand what a plane means? You gotta be honest with me. Tell me, do you know what a plane means? Other than something that's flying in the sky?
A plane?
Yeah.
Oh, no.
A plane, when we talk about a plane, we're talking about a surface. In this case, and you can see that this is a two-dimensional surface. It's like a 2D surface, just flat.
Yeah.
So I'll show you exactly what's happening. Like in 3D space. Right? Again, with momentum. So I'm going to send you a video on the chat. So this is why we say that the reflected ray, the incident ray, and the normal all lie on the same plane. So you see this piece of paper here? This is what is a plane. This is a plane. A plane is just a surface. Right, so check what I said on the chat. Let me know if you understand it now.
Okay.
So notice, isn't the incident ray, the normal, and the reflected ray all on the same sheet of paper? Yeah or no? You see, now it's on the same sheet of paper. So all a plane is just a surface. And so
It's just a surface, like I said.
we quote him that. I guess you could say that. So a plane, so the piece of paper is a plane, right? It's a plane. You can think of it like a plane. The piece of paper is a plane. And so the incident ray and the reflected ray would all be on the paper. So because all of it is on the paper, you see that the incident ray, the reflected ray, and the normal is on the same plane because it lies on the same piece of paper. Yeah. You understand it a little better now?
Yeah.
Yeah? It don't sound so. Sound like it's a little confused. Basically,
Kind of.
so if I shine a laser over here, it's going to, okay,
It will reflect. Yeah.
right. But what I'm saying is, it's not going to reflect. So two-dimensionally, if you were to look at it from the side, you just see a line. like you just see a line, it wouldn't deflect. It would literally be on the same plane. I don't know. I don't really know how to show it. Like kind of hard to show, other than what was on the paper. But just know, if you look at it from this
Yeah.
in a 3D perspective, this will be in line with this because it's on the same plane, like it's on the same sheet of paper. So they are going to be
Mm-hmm.
aligned with each other. Yeah, right. So the
Okay.
incident rate, the reflected rate, and the normal all lie on the same plane. Part two. One property of an image formed by a plane mirror is that it is virtual. State one other property of the image. So if you have a mirror image,
The same distance on the mirror.
so you have the same image and object distance, right? Same image and object distance from the mirror. And both of them will be the same one. If you're looking at yourself in the mirror, and it will be the same size,
Yeah.
unless you have a mirror that hates itself and making you look fatter than, like, yeah, right? And we also have, anytime you reflect something, you ever notice like if you move your left hand, when you look at it in the mirror, it come like you're moving your right hand.
Yeah.
So we call that
It's
lateral.
inverted.
Laterally inverted.
Yeah, that's the exact thing. Laterally inverted, right? So what? Cool. Now we need to state Snell's law, right? So I like to explain it in a conceptual manner. So we're gonna write the concept first. So Rihanna, you understand that? Okay, Rihanna, will you just travel faster in the sea or in air?
In the air.
In the air. So where you think light will travel faster?
Wait, what? I think what?
Where do you think light will travel faster? If you just travel faster in the air, why are you traveling slower
Uh-huh.
in the sea? What about the sea causing you to slow down?
The distance is too long?
No, the density.
Oh,
And the water dense? Okay, well, can you tell me what is denser, the water or air?
the water.
Okay, imagine if you had to swim in mud. You think you'd be able to swim in mud easily? You think you'd be able to move easily? Yes or no?
No.
No, because the mud is dense. So anytime
Yeah.
something is dense, it slows down your velocity or your speed, right? It slows that down. So Snell's law explains how light bends when it passes from one medium to another. You understand what I'm saying, Rihanna? You wouldn't move at the same speed in air versus water because the water is
Yeah.
denser. It's the same thing for light. Light cannot move at the same speed in air versus water, and so it bends. That's the concept.
Okay.
Right. So Snell's law explains how light bends when it passes from one medium to another due to a change in density which affects the speed of light. And it's given by this relationship. It is given by this relationship. Right. So Ni sin I is equal to Nr sin R. Some of you would have probably learned it as N is equal to sin I all over sin R. So these are different ways in which you could write Snell's law. Yeah. So Rihanna, which way did you learn it in school? Snell's law.
I learned as n equals sine I over sine R.
So this.
Yeah.
Okay. The only problem is not all the time you could use this. Not all the time. When you're using this one, you need to figure out what n is equal to. You always need to figure out what n is equal to. This one is simpler. You'll see what I mean, but you had to know when to use either one, right? You had to know when to use either one.
Yeah.
So, cool. So that's what Snell's law is. Good. So blue and red lights are incident on a perspex block as shown in figure 3. Calculate the angle of incidence for each color of light. So blue light and red light. So Justin, you're going to help me figure out the angle of incidence for the blue light. And Rihanna, you're going to help me for the red light, right? So let me hear, Justin, how are you going to find the angle of incidence for the blue light?
It could draw the normal perpendicular to the line separating the perpex and the air
Right.
first,
I like what you're doing.
and um well, from there I would like form a 90 and bisect it.
Bisected. Now, we're going good.
No?
So Justin, if that is 90, right?
Mm-hmm.
And this is 53 degrees. Is it possible to figure out what this?
Yeah,
But I'll be.
90 minus 53.
Right. Mm-hmm.
Yeah, 27.
So that's the answer for the first one. Because when you're measuring the angle of incidence, it's always with reference to the normal. Always with reference to the normal. So that's going to be 90 minus 53 is equal to 27 degrees. All right, Rihanna, help me figure out the red light now. How am I going to figure out the red light?
You have to add
What do we have to add?
the blue light and the red light.
This is not the red light, huh? That's just an angle. So that's the angle between the red and the blue light. That's the angle. That's not the angle for the red light. The angle for the red light would be what you're telling me. So they get the red light. Wouldn't this be the red light?
Yeah.
So they get the red light. They're going to add the 27, which is for the blue light, and the 17, which is in between the red light and the blue light. So wait, let's say the correct thing. Right? So that's going to be 17 plus 27, which is going to be
44.
nice. Before we move on, I want to explain a couple of things to you, right? A couple of very important things. Give a little crash course on waves and optics. So this is a go-to life hack to know. So if you're going from a less dense medium, if you're going from a less dense to a more dense, the refracted ray bends towards the normal. So Rihanna, I have a question. If it's bending towards the normal, so if it's bending towards the normal, is the angle getting smaller or bigger?
If it bends towards the normal, it'll get bigger.
No.
It'll get smaller.
If what that means, right, is that you're gonna bend towards the normal. Gonna bend towards the normal. So let me just say for the blue light, the incident ray was 27. That means you're gonna bend towards the normal, and that means that the angle of the refracted angle, when the angular refraction is going to be less than 27. So anytime you're going from a less dense to a more dense medium, like air to glass, your refracted ray is gonna bend towards the normal. And theta I, which is the angle of incidence, is gonna be more than your angular refraction. Counterclockwise, if you're going from more dense to less dense, the opposite happens. So I think you can tell me what happened in there. Tell me.
It'll be more.
Hmm. So the refracted ray would then, what's the opposite of to the normal? What's the opposite of bending towards? Bending
Opposite of bending.
should be away. So basically what I'm trying to say is, instead of wanting to go closer to the normal, it actually bends
Move
away from the normal.
further.
Mhm. Hmm. I eat a alupai there, so that's why someone kind of weird, right? So I need to know that. That's definitely something you need to know. I'm moving on. So let's check out this question. So Rihanna, read part two for me. Actually, no, Justin, read part two for me. You got to go to the next question. Justin, read part two.
Calculate the angle of refraction of the blue light, given that the refractive index of the blue light is 1.53.
Okay, Justin. So which formula are we going to use?
Um,
And
and 1 sine theta.
now you could use that formula, eh? You could use that formula, but that one a little harder because you'd first need
Oh,
to figure out the refractive index. It'd be a little harder. The easiest formula you could use there is n is equal to sine I all over
what sine r?
sine r. What is the refractive index? So n is the refractive index. So what was n? Did they tell us what n is?
Yeah, 1.53.
Right, so that's going to be 1.53. Do we know what the angle of incidence is?
Yeah,
What is the angle
wait,
of incidence?
um,
Okay, blue lights.
27.
Right, 27. That's going to be sine 27. And do we know what the angular refraction is? Or we're trying to calculate that.
I'm trying to calculate it.
Right, so that's the unknown. So I'm going to cross multiply. If I cross multiply, I'm going to get 1.53 sine r, and that's going to be equal to 1 by sine 27, which is just sine 27. I want to find for sine r first, so I'm going to divide both sides by 1.53. So sine r is going to be equal to sine 27 all over 1.53. And so plug this into your calculator. That's everybody who don't have a Casio. If you have a Casio, you could directly find sine inverse. If you have a Casio, you could find sine inverse of, well, actually, Justin, you could do it too, you know. Justin, you could do it too. Justin, you could, all you had to say is sine 27, you put that in brackets, divided by 1.53. So Justin, plug it into your calculator and let me know again for R.
Um, okay.
So that's the exact value.
.26.
Nah, Wait,
No.
let me just check something real quick. We make a little mistake here. What is 90 minus 53?
Um, 37.
Not 27. I don't know how we get 27. Right, that should be 37. I should plug it back into your calculator for me.
23.16.
Right, 23.16 is correct. Right, now for those of you all who want to just do it fast and get through in a simpler way, you could plug this into your calculator. So Rihanna, plug that into your calculator, put sine to the 7 over 1.53, and it's supposed to get 0.39. And to two decimal places. And to find for R, I just find sine inverse of 0.39. But if you want the exact answer, you could plug sine inverse of sine to the 7 over 1.53 into your calculator directly. And Rihanna, what are you getting for this? When you find sine inverse of 0.39, what are you getting? Rihanna, you let me know what you're getting when you find sine inverse of 0.39. I'm not hearing Rihanna. Justin, you got 23.16, right?
Yeah.
That's the correct answer. Nice. So Veed, let's find the critical angle. So Veed, what's the formula for critical angle? N is equal to 1 over Veed,
Sine C.
N is equal to 1 over
Sine C.
sine C. So this is the formula for critical angle. I'll also show you guys another method to come up with it in the exam if you forget the formula. So Veed, what was N? What was N equal to? What was the critical angle? I mean, what was the refractive index for blue light?
37. Is it?
So the refractive index for blue light was 1.53. So N is equal to 1.53. And so we have 1.53 is equal to 1 over sine C. So we're going to cross multiply. And if you cross multiply, you're going to get 1.53 sine C is equal to 1 by 1, which is 1. And so I divide both sides by 1.53. And so sine C is going to be equal to 1 over 1.53. And so to find for C, you'll have to find what now, Vid?
Sine 1.53.
Sine inverse of 1 over 1.53. So plug that into your calculator and let me know what you're getting. Supposed to get like 40.81 degrees, two decimal places. Just confirm that.
Got that.
You get that?
Yeah.
Okay, now I need to explain something to you, right? Vid, do you think you could get a critical angle when you go from a less dense medium to a more dense medium?
Dense and more dense. Yeah.
Nah. Nah.
Okay.
Let me explain something. Let me explain something. So this is our rule here, right? Let me just say you did not figure it out like this. There's another method you can employ, but it's more tricky. So I'm gonna also show that for anybody that did see it like that. So this is air over here. So wait, this is air. Let's just say that this is air, and this is the perspex block. Now the critical angle. So critical angle is only you only have a critical angle when you're going from a more dense to a less dense. So wait, imagine you had an incident ray coming from the perspex block. So like came out, just here came out, right? At the critical angle, and the angular refraction is 90. Yes or no? Is that something you know? All right. So Rihanna, hear what I'm saying. For a critical angle to occur, you must be going from a more dense medium to a less dense medium. So I want you to imagine you're going from the glass to air. Now at the critical angle, your refracted ray is going to be 90 degrees to the normal line. Does anybody remember the refractive index for air? Rihanna, does air refract anything? Rihanna, how fast you just run on air? And you just run normal speed on air? Like in the air, right? Like in regular space, when you're running, you just run normally. So that's like your normal speed. So what I'm trying to get at is that your speed is not changing. So I can multiply your speed by 1. So when we're talking about the refractive index for air, the refractive index for air is equal to 1. And in the question, they said that the refractive index for the glass is technically 1.53. That's what they said. And so watch this. If I were to use Ni sin I is equal to Nr sin R, I'm going to show you all how you get the exact same answer back. So we're talking about at the critical angle. So at the critical angle, and I'm going to plug in everything. So I'm going from the glass to the air. So my refractive index for the incident side is going to be 1.53. And that's going to be sine C. Why am I saying sine C? Because we're dealing with your critical angle. And the refractive index, when you go into air, is 1. So that's going to be by 1. And that's going to be sine R. So what exactly is your refracted angle? Whenever you are at the critical angle, the angular refraction is 90. So this is going to be sine 90. So we're going to end up with 1.53 sine C, and 1 by sine 90. Sine 90 is 1. So 1 by 1 is 1. And so you divide both sides by 1.53. And so sine C is going to be equal to 1 over 1.53. And we're back at square 1. So C would be equal to sine inverse of 1 over 1.53. And you get the exact same answer, which is C is approximately 40.81 degrees. Right, so I don't think much of you would understand this method, but I just wanted to include it anyways. So if you're good with this, remember that and do it in the exam. But here what I was saying, you could only have a critical angle when you're going from a more dense medium to a less dense medium. They could probably ask you about that. They could say, when does the critical angle occur? And you have to say that. It could only happen when you're going from a more dense to a less dense. So if I'm going from a more dense to a less dense, I mean I had to go from the glass to the air. And so my refractive index for this side would have been 1.53, and this I would have been C, because it's critical angle again. And on the other side, I'm going to air, So the refractive index for A is 1, and my angle there is going to be 90 at the critical angle, so sine 90. And you just work out for C. All right, so let's move on. All right. So Justin, help me with part 5A. So read 5A for me.
Write the formula to show how potential difference V, charge Q, and E, well, energy E, are related and state the SI unit for each quantity.
Right. So we have V, Q, and E. What equation you could think of that does have E, Q, and V in it?
P equals to IB.
Wait. What? That equation you tell me, does it have? It must contain V, Q, and E in it.
Oh, no.
Must contain V, Q, and E in it. So the equation that you should be thinking about is E is equal to VQ. E is equal to VQ, or you could say E is equal to QV. It means the exact same thing, and you'll get it correct. Right. E is what, Justin? What does E stand for?
E,
Yeah, E is energy, right?
yeah,
And energy is measured in,
joules.
right? Okay. Potential difference V. So V is potential difference,
It's just voltage, right?
right? That's just voltage. V, voltage. And the last one, Q. What is Q? Q is charge, and what is charge measured in?
Coulombs.
Right. C. Nice. So that just like that, you get 4 marks. A circuit can be used to recharge a battery is shown in figure 4. So we have a DC supply and we have the battery over here. On the diagram, insert the polarity of the DC supply. So they're not talking about here, right? We know that this is positive here, and we know that this is negative. Anybody here into electronics something? Anybody here into electrical engineering? Like myself?
Yes, sir.
Jadon, look easy, man. Jadon, if I want to charge a battery, right? How would I connect it? Imagine this is the battery, and I have a wire. I have 2 wires. This wire is positive and this wire is negative. How would I hook it up? Would I hook up the positive to the negative and the negative to the positive?
No, sir, you have the positive to the positive and the negative to the negative.
Right. Otherwise, I will short the battery and I pressure, right? So in this example here, the positive would need to be on this end, connecting to the positive, and the negative would need to be on this end, connecting to the negative. So Jadon, easy, right? Easy.
Yes. Oh, sir, my current is got off. That's
The current cut off.
yeah, and I think the gear Rihanna years she Wi-Fi probably got off too.
I find Ole alternating and Ole has something going on, like Ole has some mystery or something.
So I don't know who's that.
No, because like she was there whole class and then you joined back and then what? No. Something weird. All right. So part 2. Indicate in the space provided below which of the values 6 volts, 12 volts, or 15 volts is most suitable for the DC supply. So what do you think I should use to charge our battery? A 6 volt, 12 volt, or 15 volt power supply?
So 15.
Use a smart man. The reason why we can't use 6 and we can't use 12 is because for current to travel, you need to have a potential difference. And so if we use a 6 volt, that is obviously less than 12, so current would actually flow in the opposite direction. Jadon, if you use a 6 volt, the 12 volt will try to charge the 6 volt. If you use 12 volts, there'll be no flow of current because both of them have the same potential difference. And if you use the 15 has a high potential difference, and 12 volt has a low potential difference. So the current will flow from the area of high to low. And so current will flow towards the battery and it'll recharge the battery. That's the concept. So you have to use the 15. Now I think 15 kind of high. I think 15 is a little high. Ideally, if you want to show them that you really know your work, you should have said ideally 13.8, right, to 14.4 volts. If you're into car audio or anything, you should know like this is the typical ranges you deal with in car audio or anything. Because when you're charging the batteries from the alternator, you want to maintain a voltage higher than 12 to keep on charging the batteries. Yes or no?
Yes, sir.
Yeah. Right? And I'm gonna write a little explanation here. To charge a battery, the supply voltage must be slightly higher than the battery's voltage to push current into it. So in other words, current, how does current flow? So current flows from an area of higher potential difference, which is voltage, to a lower potential difference. So Jadon, it makes sense, right? If I want to charge a 12-volt battery, I would need to use something that has a slightly higher voltage, so the current could flow from the power supply to the battery.
Yes, sir.
Right. Right. Cool. Let's move on. So that was this. All right, so Jadon, help me with the electrical part of the paper. A compact fluorescent light bulb consumes 4.8 watts of power. So we see in power one time, they started giving us power, 4.8 watts. And when connected to a 120 volt AC supply, so they're giving us the voltage here. Calculate the current flowing through the bulb. So they're giving us power, they're giving us voltage. How could I find the current? What formula am I going to use?
So I realize I'll watch back the sheet.
That's okay. No, don't look back at it. Don't look back at it. We're going to figure it out in an easy manner. Jadon, you know about fast charging and thing?
Yes, sir.
And into car audio too, right?
Kinda, yes, sir.
If you want to figure out power, what are the two main things you're looking at? Voltage and
Current or there's
yeah,
power.
voltage and current. So all power is just the product of those two things. So power is equal to voltage by current. So if you want to find the power, you take the voltage, you multiply it by the current to figure out how much power your amplifier is using or how much the speaker is using. That's the calculated power. So P is equal to VI. So the power is 4.8 watts, right? And the voltage is 120 by the current. And so if I have 120 times the current and I want to find for I, what I have to do on both sides?
Divide
I have to divide both sides by,
120.
yes, you get it now. Nice. So the 120 and the 120 will cancel off. And so I would be equal to 4.8 over 120, and they should get like 0.04 amps.
Yes, sir.
All right? 0.04 amps. Right, let me keep moving on. If the bulb is connected for 5 minutes, calculate the charge passing through it. So they gave us time here. So they're giving us time. Now, Jadon, you can't use 5 as time, eh? You need to convert minutes to seconds. In physics, the SI unit for time is seconds. So if I want to convert minutes to seconds, I would multiply it by
60.
Yeah. And multiply it by 60. And so that would give me 300 seconds. And so they give us time. Jaden, I'm showing you how to figure out the formula, right? I'm showing everybody how to figure out which formula to use. It just make you find current. So most likely you gotta use that here. You see them give you time as well. So I, T, and they ask you to find Q. What formula have Q, I, and T in it? Q is equal to? Well, if you don't know the formulas, it will be hard, but the formula they essentially want you to use is Q is equal to IT. So Jadon, once you learn the formulas, this is how you're going to figure out which one to use. So watch, look at it again. They just make you find for current, they give you time, and they ask you to find for charge, which is Q. So I say Q is equal to IT. That's the formula we got to use. And so to find for charge Q, that's going to be equal to the current, which is 0.04, times the time, which is 300. So plug that into your calculator. Let me know what you guys are getting. So 0.04 by 300. For 4 marks is wild. That's crazy.
12, sir.
Wait again?
12.
12?
Yes.
Right. So that'll be 12. And the unit for charge, it sound like Christopher Columbus. It sound like Christopher Columbus.
So is it a unit for charge?
The unit for charge, this kind of sound like Columbus. Columbus.
I'm not too sure.
Coulombs, right? Yeah.
So
Charge is measured in coulombs, which is C. So 12C. Part 3. Calculate the energy the bulb transfers in 5 minutes. So we have to find for energy. And again, you see them mention time. So you need to make the link that energy is equal to power over time. That's what you need to see. So energy is equal to power by time. Power over time. Let me know if you understand that. But
yes.
we're running into a problem because we don't have power. Actually, we do have power. Watch, she said 4.8 watts. So cool, yeah, we could use this formula. So let me calculate it now. So the energy would be equal to the power, and the power here is 4.8. And what's the time?
5 minutes. Oh, I had to multiply it by 60.
Wait, I make a little mistake here, guys. Sorry about that. Watch this, right? Watch this. The formula for power is equal to energy over time. Watch that, right? Power. The formula for power is energy over time. So if I want to find for energy, energy is going to be equal to P by T. So it really is supposed to be E is equal to power, and the power is 4.8. They mentioned that. So 4.8 multiplied by the time, and the time was 300.
Yes, sir.
And where's 4.8 by 300?
One four four zero.
Right. Jalen, what if I tell you that's not the only way you could have worked this question out? You could be like, what? I'm another way?
Yes, sir. This is the only way I would think about it.
Oh, okay. And I have another method. So this other method is using the formula E is equal to VQ. Right? And that's the formula that make us use at the start. If you recall, watch. And so, tell me, what is the voltage? What was the voltage in the question?
So the voltage or the power?
Voltage. What's the voltage? 120, right? So that'll be 120. And what was the charge? The charge in this question was 12. So where's 120 by 12?
So the same 1440.
So bad physics is physics kind of like maths, you know. You can do something the same, like a bunch of different ways, and you get the same answer. So let's look at the two methods and try to understand it. So calculate the energy the bulb transfers in 5 minutes. So over here, we're using the formula P is equal to E over T. We're making E the subject to the formula. So E energy is equal to power by time. And so the power they gave us was 4.8 and the time was 300. And so we multiplied it to get 1440. Simple. Over here now, we could also say E is equal to VQ. The reason I'm saying that is because that is the equation they wanted us to use at the start. Jadon. I'm not sure if you was there for this, but they asked you to write a formula to show how potential difference, charge, and energy is linked together. And that formula was E is equal to VQ or E is equal to QV. It means the same thing. And so in the question, we had the voltage was 120, and we found charge earlier, that was 12. So 120 by 12 is 1440 joules. So either method is going to give you full marks. Yeah. Right. So we're on the last question now. Let me see if we could finish it in the 15 minutes. All right. So Rihanna in class. All right. Vid, ready for action? Like real speed? Real
Sure.
speed. All right. There's three main types of nuclear radiation,
Alpha, beta, gamma.
right? Alpha, beta, right? Gamma. And we real extra, so we're gonna write that alpha particle exists as a helium nuclei in nature. A beta particle exists as an electron in nature, and a gamma is just 0, gamma, right? Showing off your skills, right? Identify the type of nuclear radiation which forms part of the electromagnetic spectrum. Remember rich men in Vegas use expensive gadgets, right? Jason, you remember that? Rich men in
Yes.
Vegas use expensive, so yeah, X. So nth gamma was on that?
Yes, sir.
Yeah, so when you're talking about to identify the type of nuclear radiation which forms part of the electromagnetic spectrum, they're talking about gamma. So gamma. Right, Vade. Determine the type of
Alpha,
radiation that is most ionizing, right? Alpha. Alpha is the most ionizing,
and then beta.
and then gamma.
Gamma.
Gamma has the weakest ionizing power.
Oh, I took my part B.
Oh, okay.
So, so
Yeah, well,
let's do beta first.
coincidentally, it flows in the water as well. Alpha, beta, and gamma. Gamma has the weakest ionizing power.
Yeah.
Right? When we talk about made up of electrons, we looked at it here. That's beta. Right? Because the beta particles exist in nature as an electron, which is 0 minus 1 e. Right. So Justin, I'm gonna call upon you because we did questions like this in class, and you're supposed to be able to answer it. So Justin, give this question a read for me.
Fig- um, Figure 5 shows a radioactive source, which is placed in front of a radioactive detector. The average background count rate is 5 counts per second. Oh yeah, I remember questions, I guess.
Right.
With the
So
source in place, the rate rises to 69 counts per second. After an hour, the count rate drops 21 counts per second.
where's the background radiation or the background activity in this case?
5 seconds.
So to correct all the readings, what do I do?
Yeah, add 5 seconds there.
No,
Wait,
no.
wait, wait. No, wait. No, oh no, yeah, and minus it.
Right. You have
Right?
to minus it because the background. Okay, so in nature, there's some levels of background radiation, and that adds to the result you're getting. So if you want to figure out the actual radiation, you subtract the background count from the readings you get. So
Okay.
this is when you put the source And this is after hour.
Mm-hmm.
So we're gonna say, so activity of source, that is going to be equal to 69 minus 5, and that's going to be 64 counts per second. Right? Let's do after an hour. So after an hour, that's going to be equal to, so after an hour, they said it was 21 counts per second. So the corrected count rate for that would be,
21 minus 5.
right? So that's going to be 16 counts per second, and that's the activity.
Yeah.
Awesome. Calculate the half-life of the source. So Justin, here what, right? Here how we going to do this. After an hour, what happened? After an hour, it dropped to what?
16.
So look at how we're going to do this, right? So we start off with 64. Where's one half-life after 64?
32.
And another half-life.
16.
So how much half-lives that was?
2 half-lives.
And so 2 half-lives, so that taking up how much time? How long it take to reach 16?
That'll be hour.
Right? Justin, after
Yeah.
an hour. After an hour. So 2 hours, so 2 time and a halves would be equal to 1 hour. So 1
Okay.
time and a half would be equal to 0.5 of an hour. So calculate the half-life. Your half-life is 30 minutes. Because half of an hour, half of 60 is 30 minutes. Yes or no? I don't know if you understand that.
Yeah.
Right. Cool. And let's play it safe, right? The SI unit for time in physics is the SI unit for time in physics minutes. Tell me, is it minutes?
Seconds.
Seconds. So we should probably convert this to seconds just to be on the safe side. So in 1 minute, there's 60 seconds. So I'm going to convert this by multiplying it by 60. So 30 by 60 is 1800 seconds. And that's the safest answer to put. They can't penalize you in any way possible because you're giving the answer in SI units. Right. And let's move on. Right. Justin, read this from here.
A block of lead is then placed between the source and the detector. The results of the count rates are recorded in table 2.
Right. So remind me, if I remove the source and I remove the block, are there any radioactive influences on the, no. So what is the only thing the Geiger counter will pick up? The what? If you remove everything, what's the only thing the Geiger counter is going to pick up? The what? Tell me.
The block of lead.
No, the background radiation. Justin, if you remove everything, the only thing the Geiger counter is going to have to possibly read is the radiation that existed in the background. And in the previous question, it said it was 5. So the answer for the last one there is 5, right? The source is known to emit one type of radiation only. Deduce what type of radiation it is. Justin, which type of radiation has the strongest penetrative ability?
Gamma.
Gamma. So, let me ask that question. If you put a block of lead in front of alpha, what happens to it? You think the alpha will get to pass through the gamma? I mean, you think the alpha will get to pass through the lead block?
No.
No. So, and let me ask that question. If you look, I want you to look at the count rate. This was it originally, but when I place the lead block, it dropped down to 32. Did it drop to 0?
No.
No, so it can't be alpha because alpha would have dropped to zero because alpha cannot pass through a block of lead. Neither could gamma. I mean, what's it? Neither could beta, right? Beta would not be able to make it through the lead. The lead would completely block the beta. So gamma is the only one that could possibly pass through a block of lead. So the type of radiation here is gamma, right? Has to be gamma. Okay, and give two reasons to support the answer, right? I'm going to tell you what you're supposed to put for that. So number one, the count rate. So the count rate didn't drop entirely. It kind of like halved. So the count rate only dropped from 69 to 32. Jadon, I want you to understand what I'm saying, right? I'm saying that alpha would not be able to pass through the lead block. Beta would not be able to pass through it. So it had to be gamma, right? Because gamma passed through. You were still getting readings. Yes or no?
Yes, sir.
Right? So the count rate only dropped from 69 to 32 counts per second when the lead was added. Right? And what does this suggest? This suggests that the radiation was partially blocked. So I'll put that in the second part. So in the first part, I'm giving qualitative analysis. I mean, what's it? Quantitative analysis. I'm comparing quantities. And in the second part, I'm going to give them a qualitative analysis, right? So the radiation was still able to pass through. Right. So in the top part, I'm giving them a quantitative analysis, right? I'm directly comparing quantities. And in the second part, I'm comparing properties. So this is a quantitative analysis. Right, and this is a qualitative analysis. Right, so that is it. That is it. So yeah, does anybody have any questions with regards to this particular year? Via, do you have any particular questions? Or you're good?
Trying to think of one that's logical, but
Say that again?
I'm trying to think of like a logical question if I need help or something. Yeah, maybe the first one, just part B.
Part B, give you trouble. Would you do the graph?
Oh no, just like, well, telling between like step up or step down. I'll confuse it sometimes.
Okay, well, I'm gonna tell you how we like to get correct all the time, right? Listen to me. Listen to me. If it's a step down, that means it has more turns in the primary and less turns in the secondary. So if you think about it, like the number of turns is the voltage. So if it have less turns, less voltage. If it have more turns, more voltage. So wait, where are you seeing it having more turns? Primary or the secondary?
Primary.
So the primary voltage is going to be more. And if the primary voltage is more, then the secondary voltage is going to be less. And so it's stepping down the voltage. It's not hard to remember. You got this. You can figure it out. Just look at
Okay,
the show.
I
Just look at it.
memorize it now.
And look at the values here. V1 is the primary and V2 is the secondary. Like we can take any one here as an example. when V1 is 10, when you're putting in 10 volts into the transformer, what are you getting out?
1.5.
Right? So you could look at the values and see for yourself, as obviously is a step down, right? You can see that step down. Yeah. So are they good? Let me know.
Yeah.
Okay, great.
Perfect. Thanks.
Not a problem. So tomorrow, I want to pick some specific questions I think might come, and we're gonna run through that. Right? But later, everybody, hope all have a blessed evening. Bye.
Yes,
Bye,
bye.
sir.
Later.